Now let's take a look at particulate composites. So as I said, particulate composites imply particles of one phase which are dispersed in a continuous medium or a matrix of the second phase. Okay. So concrete, for instance, was a large particle composite where we had large aggregate particles which are embedded in a matrix of cement paste. Now in alloys, the particles of carbon, for instance, in the iron microstructure are at the atomic level. So in those cases, they are called dispersion strengthened particulate composites. For example, even in stainless steel, you have nickel and chromium embedded in the structure of steel, but those are again at atomic level. You do not have large grains of nickel and chromium embedded into steel. Okay? So these transformations or these substitutions are at the atomic scale. That is why we call them dispersion strengthened particulate composites. Here we are talking about 10 to 100 nanometer size particles. In concrete, if you remember, our particle sizes ranged from 75 microns all the way up to 40 millimeters. Okay? So these are fairly large sized particles that are embedded in the matrix. Again, some examples from the steel microstructure are given here. So this is a spheroidite steel. Spheroidite steel has a matrix of ductile ferrite alpha phase, again something which you would have learned previously in your steel lecture, and then there are particles of cementite, which is Fe3C or iron carbide, which are embedded in this matrix. When you have a cemented carbide, you have a matrix which is cobalt, which is ductile, okay, and you have particles of tungsten carbide WC, which are embedded into this cobalt. Okay. Then you have automobile tires. Please remember, automobile tires are made with vulcanized rubber. So you have matrix which is rubber, which is compliant or pliable. Rubber is still stiff because of the vulcanization, but you also have particles of carbon inside which make the material a lot stiffer. So carbon black, for instance, very fine particles of carbon are actually used as fillers in rubber to increase the stiffness of the material. Okay. So several examples exist from engineering applications. In civil engineering, of course, the most common example is concrete. Now what about the other kind of composites, fiber reinforced composites? Now here there are fibers of one phase embedded in a matrix of another phase. Okay. So for example, you consider here that this is a fiber reinforced composite where you have fibers oriented along the longitudinal direction. Okay. When you consider the longitudinal direction, it means that the direction along which the fibers are oriented. The perpendicular direction is the transverse direction. Perpendicular is the transverse direction. Now you can also have a scale of fibers which is very small, very short fibers. So here these are long fibers which are continuous and aligned. You can have short fibers that are still aligned but they are discontinuous. Short fibers, discontinuous and aligned. Now here this third case is when you have discontinuous and random short fibers. Examples of these, this one is very common in wood. You have continuous aligned fibers in wood. Okay. You have short fibers which are randomly oriented in fiber reinforced concrete, for instance. Of course, wood you will learn in another chapter. One example that we will see in this chapter itself is FRP, fiber reinforced plastic. Okay, we will talk about that a little bit later. As I said, loading direction can be longitudinal when you are loading it in the direction of the fiber. In wood, it is extremely important, for example, because when you are loading or when you are pulling the wood in the direction of the fiber, it has got very high strength. In the transverse direction, it will have a lower strength. Not just the strength, even the moisture removal properties will depend on the direction of removal of the moisture. So again, it is a very complicated material, wood. You will learn about that separately in a different chapter. Okay, now what are the critical parameters in the case of fiber reinforced composite? What are these fibers doing? So just imagine you have a cut on your face, right? They put stitches. They put stitches to your face. What do those stitches do? They keep the ruptured skin together so that the skin cells can grow in that gap and then you get a complete coverage of your scar. So stitches are trying to keep the tissues together and allow for growth of tissues to happen in the region that's been hurt. Similarly, fibers in a matrix, what they are trying to do is that if you have a material that is getting deformed, let's say a material where crack has happened, you have a fiber sitting inside the crack, bridging the crack, which is preventing the material from getting torn apart. The fiber is basically preventing the material from getting torn apart. So obviously the longer the fiber, the better it will hold the material together. The longer the fiber, the better it will hold the material together. So generally the fiber length has to be good enough for effective stiffening and strengthening. So fiber length should be greater than 15 times the fiber strength and tension multiplied by the diameter of the fiber divided by the shear strength of the fiber matrix interface. Very often we define the length to diameter ratio as the aspect ratio of the fiber. So if you bring this diameter here, obviously it says aspect ratio should be greater than 15 times sigma f by tau c. Okay, obviously the shear strength of the fiber matrix interface will depend upon the kind of matrix that you have. For a polymer matrix it will be different, for concrete it will be different, and so on. But at the same time you need to ensure that you are choosing fibers that have a high enough aspect ratio to lead to a effective stiffening or strengthening of the material and effective holding of the cracks together. Okay. For fiberglass, fiber length greater than 15 millimeters is needed, just an example of a material that is given here. So longer fibers are able to carry stress more effectively. So here for instance, you consider the short fiber where fiber length is less than what is required. If you have a long fiber, obviously the efficiency is improved when you have a long thin fiber. So you want a fiber with a high aspect ratio. Again, you can apply similar rules as you did in particulate composites with respect to calculating the net composite modulus or net composite engineering properties. Okay. So for fiber lengths which are high enough, you can actually apply these sorts of equations in the fiber direction, that means in the longitudinal direction of loading. So in this direction, you have modulus of elasticity of the composite equal to modulus of elasticity of matrix into volume fraction of the matrix plus volume fraction of the fiber into modulus of the fiber into a factor k, and k depends a lot on the orientation. If you have perfectly aligned one dimensional case like what is shown here, right, in that case you will have k equal to 1. If you have continuous aligned fibers, you will get k equal to 1. Okay. If you get random fibers in 2 dimensions, right, in 2 dimensions the fibers are random, k value reduces to 3 by 8. And if you have random in 3 dimensions, for instance when you have fiber reinforced concrete, right, in that case the k value is only 1 by 5. That means the component of the fiber in the composite reduces with more and more random orientation. If you have good alignment, the component of the fiber is very high, but if you have a poor alignment, the component of the fiber reduces significantly. In the fiber direction, the tensile strength can also be calculated in a similar way for an aligned one dimensional case, which is continuous aligned case, as tensile strength is equal to matrix strength into volume fraction of matrix plus fiber strength into volume fraction of fiber, only for the aligned one dimensional case. Okay, this is the same, we are applying the same rule of mixtures in this case also. Now let us take a look at specific construction applications of this component called fiber reinforced plastic. So as I said earlier, fiber reinforced plastic is when you have fibers which are embedded in a plastic matrix or polymer matrix. Now why would you want to use fiber reinforced plastic in construction, where we use steel very commonly? The idea is that steel obviously has a life that is restricted because of its corrosion. Steel will corrode eventually, and to have a structure that lasts long, you need to prevent steel corrosion. So main problem with conventional steel is obviously corrosion. You can replace this with materials that are corrosion resistant. Okay, and you spend a lot of money trying to repair corrosion. Again, Dr. Pillai may have already talked about that in his lecture on steel. So there are obviously needs for finding out materials that are corrosion resistant, and which will not degrade with respect to time. So, fiber reinforced plastic is basically consisting of very high tensile strength fibers embedded in a matrix, okay, natural or artificial high tensile strength fibers embedded in a polymer matrix. And again, the properties of the composite can be calculated from the properties of the individual phases, just like what we saw previously. Okay. So, what are the common fiber reinforced plastics? What are the common fiber types which are used here? You have glass fibers, you have carbon fibers, and aramid fibers. Okay. As you go from glass to carbon to aramid, obviously your costs go up significantly. Okay. Glass is cheaper, then you have carbon and then aramid. There are several fiber manufacturers or fiber reinforced plastic manufacturers in India, but you will see later when we talk about the applications that instead of using as a reinforcing, fiber reinforced plastic is often used for repairing and strengthening concrete structures. I will talk about that in just a minute. Okay. So, as I said, carbon fibers and aramid fibers are very expensive, because of which only glass fiber reinforced plastic can provide a cost effective alternative to steel reinforcement for construction purposes. Okay. So, here you have fibers of glass embedded in a matrix, okay, polymer matrix, and these are glass fibers. Okay, the advantage obviously of glass fiber reinforced plastic is that it will have no corrosion, okay, because it will not degrade like steel. Now, I will touch upon that again, because corrosion can have a different meaning when you are talking about polymers. Again, glass fiber reinforced plastics can be made into very high tensile strength materials. Okay. The glass fibers themselves are extremely strong, and the tensile strength of the fibers is generally much higher than that of the composite. Okay. Lightweight, the glass fiber reinforced plastic is much more lightweight as compared to steel. You are talking about densities of GFRP which are in the range of 2.5 to 2.7. Steel has a density of nearly 8. So, for the same size of bar, you can imagine that it is much easier to lift a GFRP bar as compared to a steel bar. Okay. So, you have a very high strength to weight ratio in the case of GFRP. The problems with GFRP are its brittle nature. So, it experiences brittle fracture, brittle behavior as compared to steel. It has even got lower stiffness, only about 25% of the steel. So, that means even at low load levels there will be a lot of deflection. There will be a lot of deflection. This is elastic deflection, mind you. If you remove the load, it should spring back, because the material does not have much plasticity. It does not exhibit a yielding. So, it has a brittle failure. Cost is high as compared to steel. GFRP is comparable, the other type of fibers which are much more effective, but they are not cost effective at all. Okay. Now, the problem with fiber reinforced plastic is that since it is plastic, its fire resistance is going to be poor. Of course, that does not mean steel has good fire resistance, it has also got poor fire resistance, but plastics can start degrading at much lower temperatures. You will have long term creep. In the case of metals like steel, the creep effects are very less, but here we are talking about a polymer matrix, so there will be creep effects. And the problem mainly is that concrete, reinforced concrete is a highly aggressive chemical environment for the polymer, because as we talked about this earlier, the pH of cement paste or concrete is 12 to 13, very high levels of pH, highly alkaline pH. We do not know what will happen to the polymer in such high pH levels. Many polymers tend to degrade at such high pHs. Again, this is one reason why when people talk about adding plastics to concrete, main problem is these plastics would tend to degrade inside concrete, and they may let out some toxic toxins into the atmosphere. We do not want that to happen. So, we need to treat them well before we use them. So, coming back to GFRP, of course, polymer may degrade in the aggressive chemical environment of the concrete. Again, just to show the brittle nature, what I have shown you here is the behavior of reinforcing and precessing steel. So, you can see that they have a very long ductile region of deformation, whereas your fiber reinforced polymers are simply breaking apart, right, in a brittle fashion. There is no deformation, there is no ductile elongation of the material. Stiffness, which is the slope of the stress strain graph, also is lower than that of steel. So, steel has a high stiffness, whereas the glass fiber reinforced plastic has a low stiffness. When you go to carbon fibers, stiffnesses increase, higher stiffness which is closer to that of steel, but the problem is it's extremely brittle behavior and simply no plastic deformation before failure. So in construction, we always want to design structures to have a ductile and slow failure. When you compromise in the ductility, it is not really an acceptable civil engineering solution. Okay? So this is something that you need to worry about when you start using alternative materials. Now, given that its use as a reinforcement could be highly limited, there are other applications that have come about of the use of fiber reinforced plastic. One of the common applications is the pre-stressing of bridges, but more commonly you have retrofitting with laminates of fiber reinforced plastic. Again, please remember, laminate basically means several sheets of fiber embedded in plastic which are in different directions. So you get a composite which is much stronger because it's got fibers now aligned in all kinds of directions. Okay, so these are laminates. What they do is they take these laminates and wrap them around the concrete. Supposing you get a fracture, what do they do? They wrap it with a plaster. Plaster ensures that you can't move your hand becomes very stiff. You can't move your hand or that joint which has got fractured until it heals. In the case of concrete, if there is a lot of cracking, you put this wrapping around it, so what it will do is it will strengthen the concrete within the wrapping area. Okay? Right. So again, fibers can also be used in structural composites, but for the most part we are talking about FRP applications in construction which are mainly for retrofitting with FRP laminates. Just what is shown here is again, these two workmen are basically fixing this FRP laminate on the underside of the column, on the underside of the bridge here. Okay. So you can see these laminates which have been fitted. These are strips of fiber reinforced plastic laminates which are stuck on like a glue. So what will happen is, if you have a beam like this and you are fixing this here to the bottom, for example, this is a cross section of the beam and you are putting the laminate at the bottom. So once you start bending, once the beam starts bending, the laminate will take a lot of the tension that happens at the bottom, right? And your beam will be protected. So here the laminates are wrapped around in the other direction. So this is for shear strengthening. This is for flexural strengthening, that means bending strengthening, and that is for shear strengthening. Okay, so there are various ways in which you can do this. The same thing could be also done with a steel plate stuck to the bottom of your concrete. But again, steel will corrode, right? Even a plate will corrode. Secondly, steel is very heavy, so if you can imagine workmen trying to put the steel plate at the bottom of the beam, that will require a significant amount of effort. Okay, and that is what exactly is shown here. For affixing steel laminates, you have a full scaffolding, many workers who are trying to put that up. In this case, a continuous application of the FRP laminate can be executed by just one worker, okay, and you don't really need any heavy scaffolding to support things. So these are applications that are commonly done with fiber reinforced plastics. Again, this is an example where these strips are being added so that an opening can be cut out from the slab. So for example, you want to create a new staircase inside your building, but you don't have a beam to support the weight of the floor if the slab is removed. So you are basically putting the laminate in a square arrangement and then removing the slab from within that, so that all the load that comes will now be taken by the laminate. Okay. So finally, let us talk briefly about structural composites. We talked about structural composites earlier when we had a discussion on, for example, pre-stressing, right? We talked about structural composite, because pre-stressing is also a form of structural composite. There is also steel tubes that are filled with concrete. That is another example of structural composite. So here the materials are not intimately getting combined. They are still separate, but they form a structure together and function together. So one of the common ones, as I said, is a laminate. So here you have fibers oriented in orthogonal directions which are stuck together with a glue. So that is a laminate basically, which is composed of two-dimensional sheets or panels which are having a preferred high strength directions. So wherever, in whichever directions the grains are oriented or fibers are oriented, for example wood, right, in whichever direction the grains are oriented, it will have a very high strength. So when you put randomly different orientations together and stick them together to form plywood, you will have a material that is strong in all directions. So plywood is a very common construction material, right, especially for formwork it is used extensively. So generally the direction of the high strength, the orientation of the high strength direction will vary with each layer, but when you put them together, a composite material will have very high strength in all directions. Now a composite sandwich panel is something that is formed out of external layers that are of a different stiffer material and internal layers that can be lightweight and less stiff. For instance, here you have sheets of aluminum on the faces joined together with adhesives to an internal structure that is a honeycombed structure. Honeycombed structure will provide very low weight, right, very low weight, but at the same time what happens is when this material is loaded, because of the bulk that is provided by the interior material, the sandwiched material, it will have ability to resist large deformations. Okay. So there are two face sheets that are surrounding an inner core material which is having low density. Mostly what we do is we use honeycomb material or we use foamed polymers at the core. It can also be done by, so the face plates are typically aluminum, but we can also use plywood. Okay. So these are called structural composites, and this is because the materials are combined to work structurally together. They are not intimately mixed together. So to summarize this chapter on polymers and composites, we have specific applications in construction that requires the use of composite materials, okay, and in many instances we have plastic as the phase that is present in the composites, the binding phase or matrix phase that is present in the composite. So efficiency in performance is obtained from the synergy that the different components exhibit when they come together. Individually they are performing differently, but when they come together, there is a synergistic effect that results in the performance of composite. Again, when you apply polymers and composites in construction in an outdoor environment, their stability will be governed by their resistance to ultraviolet degradation. So they will degrade with respect to ultraviolet conditions. However, the rate of degradation will determine what is the suitability of a particular type of composite for a given environment. Okay. Characterization of polymers is extremely tricky. You need to be sure that you are applying the correct rate of loading and the right temperature is being used for doing the test. Okay. As opposed to concrete, of course, in concrete also we want to test everything at the right rate of loading. However, it is not as sensitive to the rate of loading as polymers. Okay. So with that we complete this chapter. There is a good reference by this book by William Callister. It is a must have for all engineering students, I think, although it talks primarily about material science approach, but even civil engineers should have a significant understanding of the coverage of materials that you have in William Callister. Okay. So this book is called Material Science and Engineering, an Introduction. There is an Indian version available which is fairly low cost for the kind of material that it provides you. It is actually a real treasure trove to have. Any material scientist, any budding civil engineer should have that book to understand the basic properties of materials. Okay. With that we end this chapter. You will see that much of our discussion on polymers will also be valid when we discuss bituminous pavements in one of the last sections of this course. Thank you very much.